Hello, Matrix. Welcome to Trig graphs. I feel that you are going to enjoy this section because, like I said before, it's just a repeat of grade 11 theory, with slight applications of your double angle identity knowledge. But generally, the trig graphs haven't changed, and there's only one exercise to do on this work, so let's go for it. Let's play a game of who am I? Guess, guess, guess. I have a y-axis. I have an x-axis. And I go up. Oh, I fluctuate between 1 and -1. And I go uppy, uppy, downy, downy, a mountain and a valley. My period is 360 degrees. That means a full curve takes up the space of 360 degrees. So obviously half of the curve would be 180 degrees. And halfway to that point would be 90 degrees. Have a look at the cast diagram for a second. This trig ratio is positive in quadrant 1 and 2 because on this graph in front of us, from 0 degrees to 180 degrees, we see the mountain. We see the curve lies above the x-axis. Then from 180 degrees onwards, we see that this trig ratio will be negative because it lies below the x-axis. And the cast diagram, quadrant 3 and 4, in those two quadrants, this trig ratio will be negative. What could this trig graph be? Why, of course, it is the basic sine curve that we are looking at. Y equals sine x. Like I said before, the period is 360 degrees. That means beyond 360 degrees, we will see a repetition of the mountain and then the valley, and then the mountain and then the valley. The amplitude of the basic sine curve is 1, which means that the crest of this wave would reach 1 on the y-axis. And to get that value, you usually say your max minus your min divided by 2. So we'll jot that down in a few seconds as well. The range is an element of -1 to +1, smallest possible y value, so the minimum up to the maximum. And then from your range, you can see what your minimum and maximum y values would be. Obviously, this curve could repeat itself in both directions, towards positive infinity and negative infinity, but the basic sine curve, we just focus on those first 360 degrees. General formula for the sine curve includes those 4 unknowns, A, B, P, and Q. Your A is your amplitude, which is your max minus your min divided by 2. And then if A is a negative number, you must know that this curve won't have a mountain, then a valley. It will first have a valley and then a mountain because of the reflection over the x-axis. B represents the number of curves you will see in the space of the normal period. So the period is 360 degrees. So B represents the number of curves you will see in the space of 360 degrees. And if you'd like to jot down the definition of what a period is, it's the number of degrees through which the curve flows before it begins to repeat itself. The number of degrees through which the curve flows before it begins to repeat itself. P represents your horizontal shift and Q represents your vertical shift. You can get this Q value by taking your maximum, adding your minimum, and dividing by 2. You'll see that the cos graph is exactly the same as the sine. All I've done is duplicate this slide and I've changed the heading from sine to cosine. But what do we need to do in order for the graph to turn into a cosine function? Remember that sine and cosine are co-functions, complementary angles, so they differ by a mere 90 degrees. If we were to take the sine graph and shift it over by 90, we would get the cos graph. How cool is that? So here you can see I've just cropped off the curve so that it falls within 360 degrees, and you'll see that you have a minimum of -1, a maximum of +1. All the information we jotted down for sine applies for cos as well. The only difference is that the basic cosine curve looks like a bowl or a bicycle handles. Last but not least, we have the basic tangent curve. I'm sure you can remember that there's an asymptote at 90 degrees, and that will repeat itself every 180 degrees. Why? Because the period of this graph is 180 degrees. The number of degrees through which the curve flows before it begins to repeat itself is 180 for tan, but 360 for cosine and sine. Why is there an asymptote at 90 degrees? Because if you think about the cast diagram, tan is y over x. At 90 degrees, y over x would be y over 0, and then that would occur again at 270 degrees. That is why the curve of the graph of the tan function has asymptotes at 90 plus k 180. Then there's a very significant point on this graph, and that is the fact that when x equals 45, your gradient normally of a straight line making a 45-degree angle, or your corresponding y value to x is 45 would be 1. If your corresponding y value when x equals 45 is not 1, that means we've tampered with the graph, and that a value in the general formula will be different. All right, so how do we normally find that a value? We can't go max minus min divided by 2 for this one, because there is no maximum, there is no minimum. Look at how the range is just an element of real values. Jot that down because I failed to put it into the slideshow. And the range of tan will just be y is an element of r. And to get this a value, we take the y value when x is 45 degrees and we subtract the y-intercept. So we see what is that vertical distance between the y value when x is 45 and the y-intercept. In this case, you could see it would be 1 minus 0, which would obviously give us 1 for the basic tan curve. If a is a negative number, then you must realize we are flipping this tan curve over the x-axis. We're reflecting it. And so instead of approaching positive infinity along the y-axis, it would then approach negative infinity. B, like before, represents the number of curves you will see in the space of the normal period, so in the space of 180. And then P represents the horizontal shift, while Q represents the vertical shift. Again, we can't say Q equals max plus min divided by 2 because there are no maxima and minima. So here your Q is merely your y-intercept. Easy peasy.